How's everyone? How's everyone? That's the spirit. There you go. All right. So before I start, I want to make a couple of announcements. One, it was brought to our attention that some students still don't have access to Piazza. Please email Olivia as soon as possible if that's the case for you, right? And the second thing is, please start looking at homework early, okay? We would like to have you come to our office hours, homework parties, and chat with us about them. We'll also give you time to process the material as we go. We also realize that some of you said that they don't know which problems they can solve after each lecture, so we're going to start having discussion TAs tell you after each discussion what problems until now you're able to solve. So that at least helps you look at the problems. Okay? And the third thing, which is not an announcement, is a note. I want to tell you what I think the role of discussions is, and that is sometimes to discuss material that was covered in lecture, and sometimes to prepare you for next lecture. So if sometimes a new concept is introduced in discussion, this is normal in classes, especially classes that go very fast like this. So don't be deterred, okay? This is normal. This happens. Good? Spirits up? That's not good enough. Spirits up?
Yes.
Yeah, there you go. All right. So what I have on the board right now is a recap from last lecture. This is not new, okay? So you have it. I believe that's the last piece of note that you wrote in your notebooks. So I'm just going to recap it quickly so that we can start again from where we stopped. All right, so we start looking at the four fundamental subspaces of a matrix. And I said that I'm going to look at matrices of size m by n until further notice. Okay, so from now until I say otherwise, the matrix is always m by n. And then I said, okay, we can define a system of linear equations if I'm given a matrix. We've done that. We've been doing that since the beginning of this class. And I said, this is what we're used to seeing, right? So if this is the equation, the system of linear equations that I have, it has m equations based on the dimensions and n unknowns. No surprises so far. And I said, let's say that by magic I found some solution to this system of linear equations. And then I said, okay, let's introduce something slightly new. It's not new, actually. You'll see in a bit that you've seen it before. That says ax equals 0. It's a special case of this system of linear equations. I chose a specific b to solve for, right? And I said, okay, let's say I found that many solutions. We know that if it has more than one solution, there must be infinite. But that's why I said, okay, let's say that I'm just looking at some linearly independent solutions. A subset. They don't have to be all of them. They don't have to be spanning or anything. Just pick 2, 3, whatever you want, right? Make sure they're linearly independent, if they exist. Good so far? Okay. And then we looked at this claim that I made the last thing in last lecture, is if I construct a new x by adding the particular solution to any linear combination of the homogeneous solutions, that this new vector will solve the particular system of linear equations. And the way we showed it is really by just plugging in that vector in my system of linear equations, which is summarized in the last line here. And we showed that the first part is actually b, because I know xp solves this system of linear equations. And all of these are zeros because each one of the xh's is a solution to the homogeneous one. So all of these are zeros. And so b plus 0 is b. That's where we stopped last time. Good? All right, so now we take this and we move forward. We observe something that there seems to be something happening here where there's some closure that looks at us. That not only that these solve the homogeneous system of linear equations, it seems that every linear combination of them will also do so. Okay? So it seems there's a subspace somewhere there hiding. Remember, closure and subspaces. So that's what we're going to try to substantiate. And so we observe, so observation 1, I'm going to call it N1, that if I have any xh in Rn that solves the following system of linear equations, a homogeneous one, then any scaled version of xh will also solve it. Then alpha times xh also solves it. All right? Which is nothing really new. I'm going to actually show it just for this special case, but we've seen it before. Okay, so how do I verify this? Again, I plug in. So let's try to plug it in, verify. So I'll take A times my new x, or this thing, let's call it x1. So A times x1, I'm plugging in the value for x1. It's A times alpha times xh, which is alpha times A times xh. And that thing I know is 0, because I know that xh solves this system. And so A times x1 is indeed 0. Okay, let me bring that up. So just to give you some reason why I'm doing this observation, if you recall the definition, or not the definition, sorry, the theorem that we said, how do I show that a subset of a vector space is itself a subspace? I need to show three things. Two of them were closure, one under scaling, the other one under addition, and the third thing I need to show that the 0 was also in my subset. So this observation in essence is the first of the three. I'm going to summarize it in a bit, but I want to give you a peek ahead. Why am I doing these things? So this seems like the first closure property that I need to show for subspaces. Agreed? Good? So, observation 2, as you can now predict, I'm going to call it N2, and as you can predict, I'm going to try to show the second closure property. That is, if I have two solutions now, xh1 and xh2, not necessarily linearly independent, by the way. Not necessarily. Any two solutions. So both have to be in Rn, because that's the number of unknowns I have. Solve Ax. So if these solve Ax equals 0, then I define x2 to be the sum of these two. I imagine that it will also solve, and we'll verify that. So xh1 plus xh2 also solves Ax equals 0. And again, how do I verify? I plug it in. So let's verify. What is Ax2? Plugging in the definition for x2. So it's A times xh1 plus xh2. And I distribute, and I get Axh1 plus Axh2. And I know that each one of these two is 0, because each one of xh1 and xh2, each one of them is a solution to my homogeneous system. Okay? So 0 plus 0 vectors is indeed the 0 vector. And so x2 also solves that. Okay? Just to clarify, what is the dimension of this 0 vector? Nancy or mom? Nancy? This is the right-hand side of my system of linear equations. This is like the B. This has to be the same number of equations, right? Because this is the right-hand side of my system of linear equations. How many equations do I have? M. So this is in Rm, okay? It's good to keep working with the dimensions so that we understand what's happening. Okay? X is in Rn. Once I multiply it by A, the result is in Rn. Okay? Good. So the third observation, as you can also predict, that I want to show that the 0 always solves that system of linear equations. X equals 0 will always solve it. All right? So the 0 in Rn, that length, always solves Ax equals 0. Right? And that is trivial. Right? If I plug it in, verify, for completion, A times 0, this one in Rn, Nancy, 0 times, so the 0 vector times any matrix is the 0 vector, with the dimensions matching, obviously, but this one is an Rm. So indeed, it does solve. Okay? And now, it seems like I have 3 properties that match nicely with the 3 things I need to show for some subspace. So let's define that subspace and just declare that it's actually a subspace. So definition. So the null space of matrix A is defined as, so notation-wise we say null of A is defined as the set of all variables x, or all instances of that variable in Rn, such that they solve the homogeneous system of linear equations, such that Ax is 0. So I'm just taking all these and putting them in a big bag and defining it as the null space. And I'm calling it a space already, even though I still need to like just tie it and prove that it's actually a space. But we've already seen the properties, so I'm just going to write that down for the record. So theorem. So either null capital or small both work. So I'm going to do small here just to show you that both are fine. Null A is a vector subspace inside, just to clarify, inside Rn, right? So from its definition, you see that all the elements are from Rn. Okay, just to substantiate what subspace of what a bigger space it is coming from. And the proof is, I need to show, again, closure under scaling. That's property 1 in the theorem that you have in your notes. And that's exactly observation N1. So that's N1. Second, I need to show closure under vector addition. That's exactly observation N2. And lastly, I need to show that the 0 is in my newly defined set, which is exactly observation what? N3, which concludes the proof. Okay? Good? So this is what a null space is. It's the set of all x's that solve my homogeneous system of linear equations for A. Okay, so with that, let's show you where you've seen this before. You have seen it before. Anyone want to take a guess where we've seen it before? Where do you think we've seen it before? The water pump problem. When we looked at equilibrium, right? Let me write that down. So recall. In the water pump problem, we asked what state S star is equilibrium that if I multiply it by P, as in if I run the pumps once, I will still be at S, right? And then how did we solve that? We said, here's the trick. I'm going to multiply this by the identity. Move it to the other side, so I get P minus I times S star equals 0. This is the A we've been talking about, for instance, in this specific instance. So the set of solutions to this constraint, to this system of linear equations, is indeed the null space of P minus I. In other words, the set of vectors that are all equilibrium is exactly the null space of this thing. Okay, so we've seen it before. Good? And so just to remind you what the solution was, we actually solved this. And the solution was that this null space is, I'm going to write it as a span, the span of the following vector, 8, 6, 9. Why? Because we showed that all the solutions were some multiple of this vector. That's when we solved it, we had a free variable. And it showed that this is, any solution can be written like this, which means that this vector spans my null space. Okay? Okay, so now I want to ask a question. I know that the null space, because it's a space, always has the vector 0 in it. Right? And I know 0 is always an equilibrium, because 0 times any matrix is 0. But that's not an interesting equilibrium. Right? If I don't have water anywhere, run the pumps or don't run the pumps, nothing moves. So to have any interesting equilibrium, by interesting I mean something that is not 0, I needed to have more than a unique solution to this system of equations, correct? But what do we know about having more than one solution? Say in terms of columns of that matrix. They have to be independent or dependent? Dependent, right? So it seems that the kind of like number of solutions in null space depends on the columns of the matrix. See, I'm starting to connect things. So let me summarize that. But to have S not equal 0 in the null space of P minus I, we need P minus I to have linearly dependent columns, right? If I want any vector that is not 0 to be in, that's what I just said. I need the columns to be linearly dependent. But that's not only the case for P minus I. This is for any A. If I want the null space of any A to not be just a 0 vector, I better have linearly dependent columns. So let's look at that creature. And that we also have seen in lecture 1b, the second lecture. So another definition, which we've defined it before. I'm just rewriting it for completeness. The column span, in some other textbooks it might be called column space of A is, so notation-wise we call it col span of A, is, anyone remember? What was it? How do I generate it, that space? Span of the columns, right? So let's say that A is, I'm just going to give names to the columns. So that's A1 all the way to A. How many do I have? How many columns? Matrix is A m by n. Nancy or mom? Nancy, yes. I have Nancy columns. So that's nothing but the span of A1 all the way to AN. Right? And we recall a theorem from yesterday that said a span of any set of vectors is always a vector subspace of where these vectors came from. So where do these vectors come from? Our mom or our Nancy? Each one of the columns. Mom, right? So the columns come from Rm. So this is a subspace of Rm. Okay, so we've seen this, and the reason I'm defining it because it seems the null space is related to this. And this is the theme of at least the next 20 minutes. Okay? So let's start to have a an image, because we seem to have the null space being a subspace of Rn, Nancy. This is being of R mom, and it seems to start to get all over the place. So let's draw an image. So we have on one side Rn, on the other side we have Rm, and we go between them by multiplying by A. Okay? So one space in Rm is the call span. So here I have the call span of A. It's a subspace of Rm. The null space was a subspace of Rn, Nancy, right? So we're just going to draw it here. So that's the null of A. Good? We're going to keep building this image as we go, just so that we sort things out. Good? So I'll keep bringing this board down and up all the time. Okay. So now, just to do something rather straightforward from this point, since we define some space of the span of the columns of A, I want to be fair, let's also define a space for the rows of A. Right? These are also transposed vectors. I can bring them back to being vectors and span them and see what happens, right? So that's the next definition. If I call A, just to give names to the rows, alpha 1 transpose, I have M mom rows, right? So M. So these are the rows. The row span, again, could be also called row space of A, is, so notation-wise, row span of A is defined as the span of the rows this time. But I want to keep the rows as vectors, so I just will get rid of the transposes, because I like to think about vectors always as column space, columns, right? So I'll take the alphas, but without the transpose, just to keep us sane. Each one of these, where does it come from? Our mom or our Nancy? Nancy. So this is indeed a subspace of our Nancy. So in our image, that's on this part of the board. Okay. So this thing is the row span of A. Okay? Good? So let's start to try to connect these spaces as we define them. And the first thing I want to look at is another definition so that we start to put some numbers. So let's define, if I look at a matrix A m by n again, and I look at the dimension, remember dimension was the number of elements in the basis of that space. So if I look at the dimension of my column span of A, right, is called, we're going to call this, give it a name, the rank of A, and we could write rank A for it as in terms of notation. All right? So rank A is a number that tells me the dimension of the column span. Okay, so in this image here, if I look at the dimension, and if I tell you, so example, all right, let's do this here. if I tell you that the rank of A, so if rank of A is some number R, what does it mean? How many independent columns do I have? R, right? So it means that I have R independent columns. What does it say about the number of pivots? How many pivots would I have? Also R, right? So also means R pivots in my row echelon form, any row echelon form of A. Okay? So just to understand what that R means. So we know how to figure out that R. We do gas elimination, we can figure it out. So let's say that the dimension here is R, and start filling also the relationship between these two, or all of these. Okay? So, if that's the case, let's try to relate two of them that seems, something that seems quite looking at us. Let me make sure I covered everything so far that I wanted to cover. Good. So let's look at the relationship between the row span and the null space. I'm starting with this because both of them are in part of Rn. It seems like manageable. I can compare them. So let's try to do that. So we note that, we observe that if I take an x from the null space of A, and because I know that AX is equal to what? X is in the null space. So what is AX? 0. So let me rewrite that. I'm going to have zeros here. Mom of them is equal to, I'm going to look at A from a row perspective. Because I'm looking at the row span, so let's look at the rows of A. We call them alpha 1 transpose all the way to alpha M transpose, correct? And if I multiply that by x, what do I get? In the first place here, what do I get in the result? Alpha 1 transpose times x, right? This is alpha 1 transpose times x. The same thing goes all the way to alpha m transpose x. And now let's look at these creatures. And first of all of them are zeros. So let's try to put a meaning to what it means for that to be 0. It turns out that this has a geometric meaning. So far we've been looking at algebra, algebra, algebra. So let's add some visualization to it. So I'm going to define something we all know from high school, just not in this form. And that is orthogonality. Okay? We say, so if we have two vectors, x and y, in any Rn, we say that x is orthogonal to y, in words, x orthogonal to y, if x transpose y is 0. And so this 0, just to clarify, is a scalar, it's a number. Right? And so let's look at what that is from the definition. That is x1, y1 plus x2, y2 all the way to xn, yn. Right? That's just a scalar. And more on why this is the case, we'll really have a full lecture on this in module 3. Okay? But that's how I check whether two vectors are orthogonal. And we're going to have some example. Okay? Another thing that is also geometric, I can also look at the length of a vector. Okay? So let's, in the same breath, define that. So another definition. If I have x in Rn, then the norm of x is defined as, so that's the norm, the definition of the norm. We write it as x. And we've actually seen this from high school, so this is not going to be new. It is x1 squared plus x2 squared all the way to xn squared. And then I take a square root. Right? We've seen this in the 2D case, for instance. Pythagoras looks a lot like this and so forth, right? But I can write this as some vector multiplication. This is really the square root of x transpose x, if you work the definition. So kind of like square root of multiply x by itself, but just work the dimensions right, okay? Because it looks similar to this, so just to map it. Good? So these are more geometric. And now why did I mention this? Because look, these are exactly what I define as orthogonal, right? I have a vector alpha 1 and x, such that alpha 1 transpose x is 0. Okay, so let's write these down. So we have x is orthogonal. So x, let me just repeat. So x again is in the null space. Then we have x orthogonal to all the rows of A. Do you guys see it? By definition. So it's orthogonal to alpha 1, alpha 2, all the way to alpha m. Orthogonal. The same orthogonal you know, 90 degrees. Okay? So, what does that mean? So let's try to visualize it. Let's say, let's take R3, something we know how to look at. So I have R3, and I'll define two spaces. Let's call this the x axis, y axis, and z axis. One vector space I can look here for is the xy plane. Okay? So the xy plane can be defined as the span of anything that can be written as going in this direction and this direction. So I can write it as 1, 0, 0, the span of 1, 0, 0, and 0, 1, 0. Right? Anything in this plane, I can reach it using these two directions. I don't need the z, because I'm not going up. I'm not flying. I'm just driving on the ground. What is an orthogonal vector to this space? What is something that orthogonal, visually speaking? Anything that flies is orthogonal. So anything along this line is orthogonal. Okay? So what is this line? It's another space. So the z-axis is nothing but the span of what? 0, 0, 1. Okay? So now we have two spaces such that every vector from one space is orthogonal to every other vector, or every vector from the other space. We'll call these two spaces orthogonal. Okay? So why am I doing all this? Because I have every vector from the null space is orthogonal to all the rows. Right? So by extension, you can show that if I have some other vector from the row space, so if I have y from the row space, or row span of A, then I can write y as some linear combination. I'm going to call it lambda small m alpha small m, m from 1 to capital M. This is any vector in the row space can be written like that. Let's see if that is also orthogonal to any vector from the null space. How do I check? So we check. We take x transpose y. So I plug in the definition of y. So I get x transpose times the sum from m from 1 to capital M, lambda m alpha m. And I distribute, so I get the sum of lambda m, I'm going from 1 to capital M, of x transpose alpha m. And what do I know about each one of these? What do I know about each x transpose alpha m? 0. The number 0. Okay, so this is nothing but a sum of zeros. What is this? 0. Which means that x is also orthogonal to any y from the row space. Okay? Good? So we have two spaces that live in Rn, and they're orthogonal, similar to these two living in R3 and orthogonal, just to visualize things. Okay, so I can add that there's a 90 degree between the row span and the null span. They're orthogonal. I'm going to even make a stronger statement. Not only that they're orthogonal, but together, if I take the A basis for the row span and A basis for the null space, combined, they will span the whole Rn. So not only that they're orthogonal, I'm going to say that they fill up the whole space too. Okay? So stronger statement. We have that the null space, which way do you want to write it? The row space of A, and this is how we denote it, is null of A, and this is the sign. What this means is two things. First of all, it's orthogonal, and it's the orthogonal complement, meaning take the whole Rn, these two will fill it. That's what this means, okay? So in words, these are orthogonal complements. Okay, just to signify what that means in words. So orthogonal complements means this means that any vector z from Rn can be broken down into two components, can be written, this is for your own visualization, as z equal to some x coming from the null space of A plus some y coming from the row space of A. Any vector, I can break it down into two orthogonal components. That's what it means. Similar to this, R3 is broken down into two orthogonal complements. The one of them was the xy plane, and the other one was the z-axis. Together, they fill the whole space. Any vector, 1, 1, 1, for instance, I can break it down into 1, 1, 0, and plus 0, 0, 1. Right? So they're orthogonal and complement each other to fill the whole space. Okay? So, if that's the case, what do I know about the dimensions of them? If I sum their dimensions, what do I have to sum to? N, the whole thing, right? The same way that the sum of the dimensions of these two spaces sum to 3, because they fill up the whole space. So now I can even do one more thing in my picture here. So if I know that, if I just say I have some dimension for the null space, let's say it's k, then I know the dimension of the row space. What is the dimension here? N minus k. Okay? We're going to amend this in a bit. That's when we amend this, it's going to be the summary of all of this. But for now, this is what we know. I'm just filling in what we know. Good so far? So, and by the way, just something just to get us also getting used to this. If I look at the row span of A, what are the rows of A in A transpose? What do they become? Columns. So the row span of A in some textbooks is also written as the col span of A transpose. And if you work it out, it's the same thing. Because the rows become columns, and I span them the same way, okay? Just if you read any book and you see call span of A transpose, that's just a row span of A. Okay? Good. So now I define 3 spaces, and it seems something here is missing. So I have call span of A, call span of A transpose. That's a row span. I have null space of A. What is begging to be defined? Call span of A, call span of A transpose. Null span of A, null span of A transpose. So let's look at that. Let's define it. As you can imagine, I actually don't need a special definition for it. I define what a null space is, and A transpose is just a new matrix, but I'll write it down. So, because sometimes people give it a different name. The left null space of A is sometimes written as L null of A. Is defined as L null of A as the null space of A transpose, and explicitly it's all the vectors X. This time I'll fill it in a bit. R dimension we'll figure out in a bit. Okay, as you can imagine, it's on the other side, so it's going to be Rm, but let's figure it out. Where A transpose times X is 0. So A transpose, what are the dimensions of A transpose? This time N Nancy by M, Nancy by Mar, because I transposed it. So then X has to be of length what? M, Mar. Okay? And this is, by the same proof we did for null space, actually by extension, is a subspace of Rm. So that's the 4th in my image there. All right? Let me bring it up. So the reason this is called left null space, just for the curious ones in the crowd, is if I take this and transpose it, and this is again a vector, just to be clear. If I transpose the left-hand side, so what is A transpose X transpose, right? On one side, I want it to be 0 transpose. But on the other side, this is nothing but X transpose times A. So the same way that the null space was AX equals 0, seems to be multiplied by the left from X. You don't have to worry too much about it, but this is where the left name comes from. Okay? All right, so I have my 4 spaces, and so you can imagine, similarly to how the rows were orthogonal to the null space, we're going to have the columns being orthogonal because of this. The columns will be orthogonal, right, to the left null space. Similarly, it's going to be the same exact proof. So like how we had this, you can work it and see that it's the same thing. So let's just do quickly how that looks. So A transpose, the rows of A become the columns of A transpose, correct? Correct? Yes? Good. So now I have, and the columns of A become the rows of A transpose. So if the columns here, I call them A1 through AN, then I'll get the rows of A transpose being A1 through AN, right? So these are columns of A transposed. These are the rows of A transpose. So if I take now A transpose times X, and X is in my left null space, what do I get? First of all, I get 0. But from the other side, if I work it according to the row view of A transpose, I will get that the elements in this product are A1 transpose X all the way to AN transpose X. And all of these are zeros. Same as before. Now the columns of A became orthogonal to the left null space. So similarly to the left side in my diagram, on the right side, I also have this orthogonality. not only do I have this orthogonality, but the same way we made that stronger statement, it's also correct for the left null space and the column span. So let me write it down. Stronger. The left null space of A is the orthogonal complement of the col span of A, which means that their dimensions sum to what? M this time, because they're on the Rm side of things. So if this is R, what is the dimension here? M minus R. Okay, we're filling it up. And now comes an important theorem that I'm not going to prove because it goes through a very dark forest. It's called the rank nullity theorem. The rank nullity theorem, it's not trivial at first. It doesn't look intuitive at first, but I will explain it and ease you into it. But what it says is that the rank of A plus the dimension of the null space of A, and that's where the rank nullity comes from, the name, they sum to the number of columns in A, to n. It's not trivial at all, at first. But then we start to look at it and say, okay, what is the rank of A? It is the dimension of the columns of the col span of A. And that is the number of independent columns I have in A. Right? So number of independent columns. What is the dimension of the null space of A? It's the number of columns I don't have pivots in. That's the free variables, right? When we solve systems of linear equations. So that's the number of columns without pivots. But the columns that are independent have pivots. So that is also the number of columns with pivots. And now I ask you, number of columns without pivots plus number of columns with pivots, does it make sense that they sum to the whole number of columns? Each column, either it has a pivot or it doesn't. So now at least I hope intuitively that it makes sense. And the proof, by the way, just goes to formalize this, right? But this is the gist of it. So now that I know this, I can amend things here. I now related also the null space here to the column span. So if this is R, I can write, instead of K here, what can I write? N minus R, because of the theorem, right? So this became N minus R. But also these have to sum to N. So what is this? R. And now here's where the gist of the fundamental theorem of linear algebra is that the dimension of the column span, of the row span, is equal to the dimension of the column span. That's the road you go through. Okay? That's the gist of it. That's what it says. So let's write it down. So conclusion. We conclude that the rank of A, which is defined as the dimension of the column span of A, is equal to the dimension of the row span of A. I'm going to write it in words. This is the number of independent columns in a matrix. This is the number of independent rows in a matrix. So in words, number of independent columns is equal to the number of independent rows in any matrix. Try as hard as you want to make that not happen, you won't succeed. That's always going to be the case. Okay? I'll let you process it for 2 minutes, take questions and summarize it and move to determinants. Yes?
Oh, so does that mean for a matrix, the number of columns is not equal to the number of rows? There must be dependent columns.
Exactly. So I'll repeat that comment. So if you have a matrix that is not square, number of columns is different than number of rows. It means, so let's just have a special one of them. Let's say we have more columns than rows. It means the columns must be linearly dependent. Just by looking at it, I don't even have to try anything. Vice versa. If I have more rows than columns, then I know for a fact that the rows are linearly dependent. Right? This is strong. This is just telling us about the matrix without even looking at the numbers. Okay? So let's summarize the whole journey we took from last lecture until now. We start by looking at 4. Let me bring it up so that the front rows can see it also. We start looking at 4 somewhat natural spaces to define in a matrix. Take the columns, span them. Take the rows and span them. And then we realize that the homogeneous equation has this very nice property that it builds a space as well. So we define the null space of A. And we said, okay, we want to be fair, so let's do the equivalent in Rm, which is the left null space. So we defined these 4. Then we related them. We said, okay, each 2 on each side are orthogonal complements, and we showed that. Which means that their dimensions must sum to the whole space they belong in. So on the left-hand side, they must sum to n. On the right side, they must sum to m. And then we said, okay, is that over? And then we realized that there's another very nice theorem, the Bragg-Knowlton theorem, that relates things from both sides now, not just on the same side. It says that the null space and the column span of a matrix, their dimensions must sum to n, to the number of columns in a matrix. And we said that's kind of natural to see why, even though at first it seems like, whoa, weird. But it's because if we look at pivots, if we do Gauss elimination, each column either has a pivot, and then it's part of the independent set of columns, or it doesn't have a pivot, and then it's part of the free variables in the null space, right? And so if I sum these 2, I'll get the whole columns again. So that's what it says in my own intuitive words. And then I said, because it related to the 2, if I say column span is of dimension r, then the null space must be n minus r because of that theorem. But I also know that these 2 spaces on the left-hand side must still sum to n, the dimensions of them. So if this became n minus r, then the top one, the row span, must be r. And I concluded by saying, oh, the number of independent rows is r, and the number of independent columns is r. They always must be equal. This is the journey we did. So sometimes we lose the big picture in the details, but now I hope I brought it back to the big picture. Good? Again, this is not expected to be processed in lecture, right? This is years upon years of people doing studies of linear algebra, okay? And one last comment on this. This is not to be confused with the fundamental theorem of algebra. This is called the fundamental theorem of linear algebra. They have confusing names. The other one deals with polynomials. So if you want to Google it, make sure you write linear. Otherwise, you'll get a different theorem. Okay? All right, next. So now we move to something that when I was growing up, it annoyed me when I was studying algebra like you guys. And that is the subject of determinants. But we somehow figured out a very nice visual way to teach you. And I wish my professors, when I was your age, did it the same way. So hope you enjoy this better view of determinants. So one thing I want to comment on, for those who took linear algebra before, you know determinants with things like cofactors and whatnot and recursive definition. Please throw that out of your mind for a bit, because if you keep thinking about that while I discuss what I'm discussing, you'll be at a disadvantage to those who haven't seen it, okay? So please try not to think about it. So determinants. First, I want to say, why am I studying determinants? So there are a few things that are actually very exciting. Starting from tomorrow, I'll just want to motivate you because it may seem a bit dull. Starting from tomorrow, we're going to start looking at the algorithm that made Google great. It's called PageRank. And part of it is studying these equilibrium states that we dealt with. And part of figuring out these things and proving that the algorithm works properly goes through determinants. So that's why I want to do determinants, so that we have a clean start from tomorrow, okay? And I might not finish all of it, but you'll have way more than enough for today's discussion. I might actually also finish it. We'll see how it goes, okay? So bear with me. The rainbows are in the end. So we're going to go through that forest, but in the end there's a rainbow coming. Good? Spirits up. Good? Yeah. No, not good enough. Good? Good. There you go. All right. So instead of looking at a very mathematical, as an expression-wise definition of determinants, I want to do something more axiomatic. Same thing kind of we did with vector spaces. I'm going to write 3/4, depends on how you look at it, axioms. And I'm going to say what kind of functions satisfy these axioms, and from that build determinants, okay? So we're going to take an axiomatic approach, and I'm looking for, oh, by the way, something very important. Remember I told you until further notice we were looking at A m by n? This is the further notice. Now we're looking at square matrices. Until further notice, okay? So from now on, square. Okay? So I'm looking for a function that takes square matrices as input, right? Seemingly complicated matrix function, because it takes not square matrices of only size 2 by 2. The same function needs to take 2 by 2, 3 by 3, 4 by 4, blah, blah, blah. It's a complicated one. Right, so I'm looking for some function like that that takes a matrix in and outputs, I almost wrote spits, outputs a scalar. Good? And that thing, I want to give you some, first I'm going to write the axioms, and we're going to give you some visualization to what it means, what that function should look like, okay? So let's start with the axioms. So we're looking for a function, not only that does that, but also satisfies the following axiom. Axiom 1. Oh, by the way, just to ease myself, so in terms of notation, I'm going to mostly use this notation for determinant. So determinant of matrix A is denoted with bars. Sometimes I may write det of A, or TAs might do that, or the notes. You're free to use whichever you want, okay? Just going to stick to this because it's more concise for the board. So axiom 1. I want the determinant of the identity matrix, any identity matrix of size n by n, to be, what do you expect it to be? Think about the 1 by 1 case, the scalar. Determinant is somewhat like, imagine it's like the size, the volume of something, right? So what is a natural definition for the determinant of the scalar 1 to be? 1. So this is the extension of the 1 for the n by n case. So I want it to be 1. Axiomatically, I'm just saying I want that. Axiom 2. So as opposed to just any volume that we're used to, and again, I'll keep repeating volume, we'll see some visualization in a bit, I want to also store the directionality if I flip something. So I want that volume to be signed volume. So to capture that, I'm going to say that if you have a matrix A and you perform a single, just one, row exchange on it. So let's say that you got from A to A hat through one row exchange, Ri exchange with Rj, where I is not J, so I actually did exchange. I didn't exchange the same row with itself. That wouldn't be an exchange. Then I want to flip the sign of the determinant, because I want to keep track of this directionality, okay? So I want the determinant of A to be whatever. So I'm looking for this function that called determinant. I'm looking for this. I'm putting properties for it for now. But I want this to be negative of the determinant of A hat. Just flip the sign. So small exercise. What if I flip even number of rows? So I do row exchanges, but even times. So if I do it once, it flips the sign. What if I do it again? Flips it back, right? So this is how it plays. Every time you exchange rows, it flips it once. Good? And the third axiom, I'm going to split it into two subparts. That's why I said you could look at it as 3 axioms or 4, depends on how you count. But it's touching, so let's write axiom 3. It has something to do with something that looks like linearity. But it's not the normal linearity we're used to from transforms. I'm just going to write it's linearity in rows. So just per row or per row. Okay? So part A, if I take a matrix and I scale one row of it, only one. Okay? So if I take a matrix, it has rows alpha 1 transpose, alpha I transpose, all the way to alpha n transpose. And I scale, hope this shows, I scale one of them by t. Okay? I want the determinant as, so the original one without the scaling is A, and I'm going to write it down in a bit. So this is the original one, alpha 1 transpose, alpha I transpose, alpha n transpose. The one without any scaling, this is my A. So this is the determinant of A. And this is kind of my A hat, right? Just to think about it. I want to scale also the determinant by the same factor t. Okay? This is another axiom. It looks like linearity, right? This is a function where if you apply t to one of its parameters in a way, the t can come out of the function. That's why I call it similar to linearity. If you don't catch that analogy, don't worry too much about it. Just treat it as dry as it's written for now. We're going to visualize it in a bit. What do you expect the next one to be? So if I said linearity, for those who caught that analogy, what would the next one be? So scaling and addition. The next one I'm going to do is exactly that. So axiom 3b, still part of axiom 3, is, so this is, by the way, for all, this is for all t in reals, any scaling, including the 0, by the way. Okay? So the next one is if I start from a matrix, alpha 1 transpose alpha I transpose, all the way to alpha n transpose, and I take one of the rows and I add to it a vector transpose, again, to keep just the dimension. So if I add to it some, not necessarily other row here, some really random row that I choose, okay? So I'm going to call it, what did I call here? B. So I add to it some B transpose. By the way, can you see that blue in the back? Anyone can't see it? Say abracadabra, please. No abracadabra, so good. So the determinant of this, I want to relate it to the determinant of the original matrix without that addition. And I'm going to say it's a sum of two determinants. That's what I want. Again, linearity, similar. So the first one is nothing but the determinant of the original matrix, alpha 1, alpha I, alpha n. So this is the determinant of A. And I want to add to it the determinant of the same matrix, except now, again, it has to be kind of symmetric. Anything, all the rows are the same, but instead of this row, I'm going to just have B. So I'm going to split this into two parts. The alpha I part, that's an I, and the B part. I want to sum these two determinants. So alpha 1 transpose. This time, I want B transpose. So this is in the ith row, right? All the way to alpha n transpose. Okay? These are the three axioms I want. Now let's try to figure out what kind of functions satisfy these. But before, I actually observed something. that just by knowing these three, I can calculate the determinant for a lot of functions, for a lot of matrices, excuse me. Anyone can see why? Take a wild guess. Even it's fine. Let's do it a brainstorming. Here, I'm joining the crowd. Who wants to help? Yes. What do you think? Yes, row reduction to the I. And when can I get to the I? In what matrices? Well, yeah, but any matrix. What if the columns are dependent? Can I get to the I if I row reduce? Can I get to the identity for if I have a matrix A with linearly dependent columns? Can I row reduce it to the identity? No. So anything that has linearly independent columns, I can reduce it to the identity. I know the determinant of the identity is 1. And I know each operation, row exchange, scaling, and addition, how it affects my determinant. Right? So I know how to get there, and we'll do an example in a bit. But to make it easier for you, rather than to have to keep thinking what each one does, we're going to write a bunch of properties. But before I do that, I want to give you a promise, some visual representation of this function. Turns out that this determinant business has, I kept saying the word volume all the time, has that type of interpretation. So let's start for that intuition. So intuition. For the intuition, I'll do things in 2D because it's hard for me to draw more than 2D. So I'll do 2 axes. And I always start from 2 vectors, the elementary vectors. So this is E1 and E2. So this is the one here and this is the one here. Okay. The number 1. So this vector is 1, 0, 0, 1. Good so far? If I complete this by creating a parallel for both vectors, I get some sort of a square. That square has area what? What is the area here? 1. Good? Now, let's say that I take this and I apply A on it. So I have a matrix A now and I want to apply A on it. So what does it mean to apply A? How did I create this square? I took both vectors, created a kind of a paralleloid out of it, which happens to be a square in this case, calculated its area. So if I take these 2 sides separately and multiply each one of them, so by A, so that's making this one side, right? I'll get another vector. So this is now my new side. So this could be, say, this vector. I'll give an example with actual numbers in a bit. And if I do the same, so this is, let me write it closer to it. So this is how I will visually transform my square. So this will be A, E1. And if I do the same to A, E2, I'll get something like, I don't know, this, say, A, E2. I can also create a paralleloid out of this by similarly copying this here and copying this here. This is another one. The determinant of A is the area of this paralleloid. This is the determinant of A. Again, with keeping track of the signs. What does it mean to keep track of the signs? If these flipped after I multiply by A, see there's an order of E1 and E2. If after multiplying them by A, they flip somehow, that's where the negative sign comes in, just to keep track of that flipping. I'm giving you intuition here, okay? So that's all it is, intuition. Okay? So let's do an actual example with numbers before I continue with figuring out what this function looks like. So, where's my example? There you go. A is 2, 1, 0, 1. Okay? So let's draw the new paralleloid after I multiply the elementary vectors by A. That's what I want to figure out, the area of the unit square after I transform it. So let's figure out how that looks. So what is A times 1, 0? Right? It's 2 times 1 plus 1 times 0. And then the second entry is 0 times 1 plus 1 times 0. 0 times 1 plus 1 times 0, and that is 2, 0. Agreed? Just multiplying matrix vector. So 2, 0 is, here's 1 unit, and here's 2. So my first vector here, this is A times E1. Alternatively, you can look at it. This is a linear combination of the columns of A with the coefficients being these things. So I'm actually picking the first column. That's why it's the same. You can look at it that way. That's actually easier to look at it that way. I'm picking the first column. If I take A times E2, which is, let me write it explicitly, 0, 1, I'm picking the second column. You can do the math or you can rely on this. This will be 1, 1, the second column of A. What is 1, 1? So let's draw it. I have 1. So this would be A, E2. Agreed? And now I complete the paralleloid. I copy this. So I'll get to 3. Agreed? Because its length is 2. So I copy it from 1, it'll get me to 3, and I complete this. And now I ask you, what is the area of this? So now high school. I have the base of length 2, so base is 2. And what is the height? 1. So what is the area? 2. And since I didn't flip the order of E1, E2, it will be 2. See, if I flip them, and that's the next example. If I flip them, and so flipping them would be A is 1, 1, 2, 0. We know that AE1 is like selecting the first column of this. This is 1, 1. So let's draw it. Okay, so this one would be 1, 1. So this would be AE1. So it's the same as here so far, but remember, they're flipped. So this is the 1, 1. And AE2 is like selecting the second column from A, which is 2, 0. And that is this. So it's the same exact paralleloid, right? Looks, at least visually. Except this time I flipped the order of the two. I kind of flipped the paralleloid. And because of that, we want to capture that, and the determinant here will be -2. This is intuition. This is not how you're supposed to calculate it. I'm just giving you intuition. How to calculate it? This is the next 6 minutes, okay? Part of it, and we'll finish it tomorrow, but the next 6 minutes will be enough for you to do the discussion today. Good. So, in our journey to find that function that satisfies the 3 axioms written up there, I can say a lot of things about it without even knowing what it is, just by these. I can extend these axioms into more properties. So property 4, and I'm counting 4 because these are also properties given to us. Now we're going to want to extend them. So the fourth property will read, if A has 2 equal rows, what does it mean if it has 2 equal rows? So let's work an example here. So B is 1, 1, 1, or 1, 2, 1, 2. If I draw that paralleloid, it will be the vector 1, 1 and the vector 2, 2. Does it have any area? No, it's clamped. Do you see it? I don't have a paralloid anymore. So I expect this to be 0. And I will show you that it is indeed 0. So if I have equal rows, then the determinant of A is 0. So proof. And I'm going to do most of these proofs in the 2 by 2 case, but they're the same. They're easily extendable to the n by n case. So I have a matrix that has AB, AB. And to visualize things, I want to give these rows names of colors, AB. So the blue AB and the white AB. What happens if I exchange rows once, according to axiom 2? If I do a single row exchange, what happens? I have to bring a negative sign out, right? Right? That's what axiom 2 says. So that's all I know. So I'll do it. I'll switch the rows. The white row goes here, and the blue row goes here. I get a number, whatever it is, r, is equal to negative r. What is the only number that satisfies r equals negative r? 0. I will conclude that this has to be 0. And you can easily see how you can extend this to the n by n. Just exchange these rows that are the same and you'll get the same thing, okay? So there's another property that we figured out. Let's do another one. I need exactly time for another one and you'll be ready for discussion today. Good. So property 5. So property 5. If A has a row of zeros, has a rows that is all zeros, what does it say about the determinant of A? Again, similarly, from visual representation, means I also clump the paralloid. I don't have a paralloid anymore. Okay? So I expect the determinant to be 0. And let's prove that. So I will start looking at this 0, 0, AB. And I will write it as 0 times some number T1, 0 times T2. I'm allowed to do that. Pick any two numbers. That's still 0. 0, 0. And copy AB. And now, so far I didn't use any axioms. I just used arithmetic. Now I'll use 3A. So axiom 3A says that I can, if I scale a row by any number, including 0, I can bring that scalar out and look at the determinant of the remaining matrix. So that would be the 0 coming from here times the determinant of the rest of the matrix. T1, T2, A, and B. That is any number. It doesn't matter. It's times 0. That's always going to be 0. Okay? I still don't know what that function is, but I could say a lot of things about it. Okay? So to summarize it, and then I'll let you go to discussions, and I have exactly 1 minute to do so, and that's enough for me. Here's the process that we do. We start from A, right? And we row reduce for now to the reduced row echelon form. And we have two cases. We either get the identity, well, let me write it down actually, the identity here, or we get some row of zeros. If I get row of zeros, what do I know about the determinant? 0. That's property 5. So that is easy. Determinant of A is 0. If I get to the identity, I know how to calculate. So I know that the determinant here is 1. So this is determinant. I can work it back or figure out every step that I did to go back to A. And each time I did something, it's either I took a scalar out, if I scaled a row. If I exchanged rows, you'll work it out in discussion what that means. Right? And if I exchange, it's a negative sign. So I know how to go back. I'll aggregate all of them and I'll get the determinant of A. And this is how we're going to calculate determinants in this class. All right? So we're going to continue from this point on tomorrow, but this is enough for you to do discussion today. Thank you. See you tomorrow.